Begin now with Paola Cessi lecture.
Okay, so this is going to be maybe a little bit technical, but this is what we use now to look at the large-scale circulation, and it took me quite a while to understand it, so I'll try to explain it to you. And this is a view from our institution, just in case you wonder. Not from my window, but close. So the motivation for using a different diagnostic to look at the atmospheric and oceanic circulation, I think, comes from this observation that if you look at the zonal mean that is averaged in longitude, meridional velocity at constant height or pressure, then you see these okay, so here in this figures, the northern hemisphere is here and southern hemisphere is here. Normally we use the other way, but anyways. So there's these cells here, they're Hadley circulation, where obviously air is ascending where it's warm near the equator and descending where it's cooler. At the edge of the subtropics around 30 degrees. And so that's all right. But then you have these funny cells, the Farrell cells, which apparently are transporting heat, if you believe this circulation, the wrong way. That is, since usually these lines here are potential temperature, these dashed lines, so clearly here it's warmer than at the bottom, so they're transporting heat towards the equator. It's like giving money to the rich people. That's not a good thing, in my view, at any rate. It causes instability. So what's going on here? Well, this apparent thermally indirect circulation goes away if instead of doing this average at a fixed height or pressure, you do that at a fixed level of potential temperature. So the potential temperature here, you only see the zonal average, but of course it has undulations in the longitudinal direction. And so if you do averages following one of those following isentropes for each isentropes, then you find that the Hadley circulation stays about the same, at least it has the same sign, but the sense of circulation in the Farrell cell is the opposite. And in fact, if you're interested in the transport of potential temperature, this is what you should be looking at, not this. Okay? And so what you're looking at, in fact, is two different measures of transport. In this case, you look at the velocity, which is, well, perhaps in the atmosphere not exactly incompressible, but close to, well, inelastic, but similar to incompressible. And so what you're looking at when you take the zonal average of the velocity really is the volume transport. Whereas here, you look at in some sense, at the average transport of potential temperature that I've indicated with rho. And so you're actually looking in some sense at the correlation of velocity and potential temperature. And so in this case, this is more indicative of the potential temperature transport than this is. And as I said, they're opposite in sign in the mid-latitude. And so this apparent transport of heat towards the equator here is not really happening. There is, in fact, poleward heat transport even in mid-latitude. Now, so first of all, let's try and understand why the Farrell cell in the Eulerian framework is thermally indirect. So when you take the zonal average, obviously the average or integral in x of dp dx in a periodic domain like the atmosphere is 0, because you come back to the same point. And so the zonally average meridional velocity cannot be balanced by the pressure. It's completely ageostrophic. Okay? And what instead is driving it or is balancing it is either frictional terms or Reynolds stresses. Here they're written in spherical coordinates, but essentially this is d by dy of u prime v prime. And similarly, since of course in a meridional overturning you have meridional velocity and up and down velocity, similarly the zonally average vertical velocity is driven by, of course, diabatic terms, heating and cooling, and this comes from the conservation of potential temperature equation. Okay, so n square is the Brunt-Weiseler frequency. And when you zonally average and time average, all the other terms really go away. And that is maintained by a combination of the adiabatic terms, heating and cooling by incoming radiation and cooling by outgoing long wave radiation, and then transport of heat by structures that don't have, the prime here refers to departure from the zonal mean. Okay, so these are eddy transports. Now in the upper part of the atmosphere, the frictional terms is very small. That really only is really only important at the bottom. And it turns out that the divergence of the Reynolds stress is negative, and I'll show you why in a second. And that therefore that drives a mean zonal circulation. This is northern hemisphere view that is equatorward. And of course it has to be accompanied by an upward motion here, where again in mid-latitude this term is not very large, and of these two terms this dominates away from the surface, and in this there's convergence of heat transport by eddies, by structures that don't have a net zonal mean, and here you have divergence. And of course, since the flow is approximately incompressible, the zonal average meridional and vertical velocity have to be non-divergent. So let's try and understand why this term here is negative. Okay, so what is happening in this location, which is at around 45 degrees north and south, is that that's where you have the maximum temperature gradient in the atmosphere. And in mid-latitude, that generates baroclinic instability, which produces cyclones and anticyclones that form our weather system. And then, since this is the region where they're produced, then they are radiated away north and south through the waves that are appropriate for nearly geostrophic motion, which are Rossby waves. And then, so let's look how a Rossby wave generated here and then propagating north and south, what property does it have? So you have a Rossby wave of the form, a plane wave, the simplest kind, e to the ikx Ly minus omega t. And Rossby waves have this dispersion relationship where this is the mean flow, this is just a Doppler shift term, and then this term's minus beta k, k squared plus s squared, where beta is the gradient of the Coriolis term with latitude. Okay, and that's positive. So in the absence of a Doppler shift, Rossby waves have a phase speed, which is always westward. But what we're interested in here is the group velocity, because that tells you if you have a packet of a wave in a certain position, how energy radiates away from that. And then some simple algebra shows that the group velocity is equal to this combination here, beta KL divided by k squared plus L square. But the important thing is it has this KL term here that can be either positive or negative depending on the wave numbers. We can also calculate from this form u prime and v prime, and u is minus d psi dy and v is plus d psi dx, so that brings you down on minus IL, and here plus IK. So then if you look at u prime v prime, this has some absolute value of c times minus KL. So it is proportional to minus the group velocity. This is the essential result. That if you have Rossby waves generated here, those that propagate northward will have negative u prime v prime correlation. This, remember, is a zonal and time average. And those that go to the south will have a positive u prime v prime. So that means that you're going from a place where you have positive u prime v prime to negative u prime v prime, because it has the opposite sign of the group velocity. Okay, so here you're going from a place where group velocity is negative to a place where group velocity is positive. But for u prime v prime, you have to change the sign. And so that means that there is convergence of Reynolds stresses, and that forces this meridional velocity at the top to be negative. Then everything else has to follow by just continuity. So that is what maintains, so away from the surface, this is the balance, and this is what maintains this equatorward mean flow. Now, what we're really interested in is the net heat transport, which is a combination of the transport by the mean and the transport by the eddies, which of course amounts to that diabatic term. And that is actually a very small residual between two large terms cancelling. And because of the continuity, you can use the momentum balance together with this, and then you have a requirement that the meridional gradient of this combination of Reynolds stress convergence and vertical gradient of buoyancy transport weighted by n square balances the heating and cooling and the frictional terms. And now it turns out that this quantity is the meridional gradient of the potential vorticity fluxes of the eddies. So to know about these small terms, because they are very small, you have to look at the potential vorticity flux divergence. And this is the flux of relative vorticity, and this is the flux of vortex stretching term for those who are familiar with the quasi-geostrophic stratified PV equation. Okay, So now there is a framework to put all these information together, and so we can look at this by looking at if we can get more insight about the mid-latitude circulation by looking at the quasi-geostrophic potential vorticity equation, where we just have, well, really one variable, psi, and the PV, and they're linearly related by this inversion, where if you know the PV, you can get psi by inverting this equation, of course with boundary conditions. And now, in general, if the flow obeys quasi-geostrophic dynamics, and around the Ferrel cell, if you ignore humidity for the moment, it's a reasonable approximation. And usually we're interested in the large scale, and in this case, perhaps zonally average, but certainly large scale, maybe time average flow. And in order to find out what the flow is, psi bar, you need to know q bar, which is linearly related to psi bar. But of course, you also need to know the divergence of the eddy fluxes of PV. The correlation can arise by having correlation of quantities that have zero mean, but there could be a correlation between these two terms. So if you want to know the mean, you need to know these fluxes. And actually, because this inversion requires boundary conditions at the top and the bottom, usually this in the atmosphere, this would be 0 at the top, at the bottom, or not. If there's topography, there would be a topographic term. So in addition to, and this is the heating and cooling at the top and bottom, but you also need to know the correlation of u prime psi prime z, which is actually the same as the buoyancy or potential temperature or whatever your isentropic quantity is. So you need to know the PV fluxes due to the eddy and the buoyancy fluxes on the boundaries also due to the eddies. And in general, the PV fluxes are given by a whole lot of terms. Here's the one we saw before, the Reynolds stress convergence, the vertical derivative of the buoyancy flux, and then there are these other terms. Not sure what their names is. But if you take the zonal average, which is certainly what is of interest in the atmosphere, they go away because they are perfect X derivatives. And so the potential vorticity flux are a combination of what we saw was driving the Ferrel cell, the convergence of the momentum flux and the vertical derivative of the buoyancy fluxes. Yes?
I don't know. So as compared to the tutorial yesterday, you didn't include the beta effect in the potential vorticity. Is it negligible here?
Did I? No, I think I forgot to write it down.
Okay. So
I simply forgot to write it down.
Okay.
But no, it's not negligible. I just forgot to write it down.
Okay.
Sorry. But since I'm going to talk about the eddy component, that doesn't enter the eddy component because it's part of the mean PV, which is not what we're interested in. And so you might think this is perverted since you have a scalar v prime q prime, but meteorologists like to write this in terms of the divergence of a vector whose components are in the meridional direction minus the Reynolds stress, and in the vertical direction the buoyancy flux is divided by the mean stratification. And then when you do they do that because then you can write the momentum equation. Well, this is just the thermal wind approximation for the velocity in the xy direction. This is the u momentum equation, and you see again in steady state, where this would be 0, you'd have a balance between the mean meridional ageostrophic velocity, the convergence of Reynolds stresses and friction. And for the buoyancy equation, again, you have the vertical transport of mean stratification, and then the convergence of buoyancy transport or entropy transport, and the diabatic term. Now, it is useful to rewrite this equation by defining a velocity in the vertical direction that is w bar plus this term divided by n square. Okay. And then this equation just tells you that that is what is balancing in steady state, that is what is balancing the diabatic heating. Or if you have time dependence, that would be balancing diabatic heating plus time dependence. Now, we're in two-dimensional flow now because we have averaged in the zonal direction. So that, to make this new velocity incompressible with the meridional component, you have to rewrite the a new velocity, which is called residual velocity, as the Eulerian velocity plus this other term. And then when you do that, again in steady state, you have that this the Coriolis term is balanced by the potential vorticity fluxes and whatever frictional term there is. And the potential vorticity fluxes is the divergence of this vector, which are called Eliason-Palm fluxes. And meteorology like to draw these vectors, and here's an example. And here's their divergence, because really that's what we're interested in. And you see that here the divergence is negative, so it drives a flow which is positive, right? In steady state, you would have F naught V star, that's the residual velocity, is equal to minus the PV fluxes. So this is the PV fluxes, which is the same as the divergence of these vectors. And it's negative, so that drives a flow which is poleward, aloft, and equatorward near the ground. Okay. So that's how you go then with this construction. If instead of plotting the stream, so here's again the stream function. Just look at the colors, these beige and light blue. See here again is the stream function associated with the mean flow. Okay, and again, here are these wretched Ferrel cell that, you know, they bring money to the rich. They're thermally indirect. And instead, if you plot the stream function associated with these residual velocity, well, the Ferrel cell stays about this. Sorry, the Hadley cells stay about the same, but the Ferrel cells change sign. Okay. And then there's a nice way of, there's a very nice identity that you can show, even in the time-dependent case, eliminating U and B bar by taking some appropriate combination and using thermal wind. You can get a nice equation, a nice elliptic equation that tells you what the residual overturning stream function is in terms of the mechanical forcing or mechanical friction, the diabatic heating, and of course you need to know the PV fluxes structure. So this is, I think, yes, and okay, yes. And so from this equation, different terms dominate at different levels. So in the upper part, in the upper branch, you have that the residual flow is balanced by the PV fluxes, whereas in the lower branch is balanced by frictional terms. So and the main thing is that it seems like a lot of work, but it's kind of beautiful the way it works out. But seems like a lot of work, but the reason why you should look at this rather than this, so the residual flow or the residual stream function rather than the Eulerian stream function, is that this is more representative of the transport of traces and not just potential temperature. Really, it is representative of the transport of all tracers than this is. This is representative of the transport of volume, but we don't really care about that very much. We care where stuff goes. Okay. So in the QG case, so I think looking at the residual circulation resolves this apparent puzzle of equatorward heat transport by the Ferrel cell. And what it's saying is that in mid-latitude, the transports of both buoyancy or potential temperature and momentum are important in maintaining these Eulerian cell. But this machinery, which is called, maybe I never said the word, but it's called transformed Eulerian mean. This machinery, I think, resolves this puzzle in a simple QG framework, and I think it's a breakthrough of showing that, in fact, the transport of stuff is opposite from what you'd see if you look at the Eulerian circulation. Now, as usual, yes. Oh, yes. Sorry, the question was, is there an easy way to explain why there is downward flow in the equatorward branch? I think this is what... yes, I think so. So usually the baroclinic eddies tend to transport heat poleward. So they would have V prime. Yes. Oh, why is it 30 degrees? Okay, so that has to do, and you know, I'm an oceanographer, so maybe the meteorologist can help me more here, but this is where you transition from the Hadley circulation to the sort of mid-latitude eddy-driven circulation. And so this is kind of the break point where eddy dynamics become so the point here is, first of all, that in the Hadley cell area, the Eulerian mean flow is representative of the residual flow. These flows are about the same, at least qualitatively. And so you don't need to worry about eddy dynamics. You solved your zonally average equation, forgetting about the PV fluxes, forgetting about the Eliason-Powell fluxes, and you're good. And so the dynamics of the Hadley cell is governed by, at least in the upper branch, by conservation of angular momentum. And that continues until you run into the area where eddies become important. Okay, and that happens at around 30 degrees. Now, why that happens to be also the place where half of the Earth is north and half is in between the tropics. I'm not sure if it's a coincidence, because I am pretty sure that in other climates the size of the Hadley cell, and even in our own future projections, of Earth climate, the size of the Hadley cell changes. So I don't think it's some mysterious, there's some universal reason for happening at 30 degrees. But that's where the dynamics of these two sort of meet. Yes.
I have two questions. One is that does it mean that the volume is transported equatorward in the mid latitudes, but the tracers are transported poleward?
Correct.
And the second question is that when we look at from the transformed Eulerian mean perspective, so there is this a small gap in between the Hadley cell and the Ferrel
That's
like
right.
so-called
You're right.
Ferrel cell.
Yes, you're
so
right.
what is happening there?
Yeah, well, so what is happening is that as you see, the height of the cell is shrunk quite a bit, and I think what is happening here, that the flow tends to be a little bit along the isotropes, and so it has a hard time crossing it, but I'm not sure why that would be here and not there. So there's no doubt that, so what is happening in the higher part of the Ferrel cell is that there is a cancellation between the Eulerian flow and the eddy part of the component, and so that reduces the height. Now, why that is physically, I'm not really sure. I don't know, actually. Yes? But maybe the more meteorological...
just one quick thought. That gap is because the water vapor. If you plot everything
there you
on
go.
the moist isentropic, there's not a gap.
Okay,
Yeah.
I see. All right, there you go. Thank you. Okay, so now transformal mean is quite simple, I think, and sort of straightforward in the quasi-geostrophic framework, and to me it seems like quite a breakthrough in the understanding of the mid-latitude circulation. But as we know, in QG, the isotropes, which they can be potential density or potential temperature, are horizontal, because you have to assume that there is this very strong basic stratification that depends only on the vertical coordinates, and which obviously is not true in this picture. Well, here are some isotropes, they're definitely not vertical. And so there is no difference between diabatic and vertical transport. But in general, isotropes are not horizontal. And so if you want to use them in situations where the QG framework is no longer applicable, then that needs to be generalized in the primitive equation. And that was done really quite recently. And so let me give you an example of how that works. So let's take an example where you don't need really all this machinery, because the flow is steady and 2D. So if you want to take the zonal average, well, you're already in 2D. And if the flow is steady, then you don't have to take the average. So this is your buoyancy equation, and then there's some other equation, that the vorticity equation, that will determine the stream function, but never mind that. So if you want to look at the buoyancy balance, that's just given by, so there's no time dependence, the flow is two-dimensional, so it's completely described by the stream function. So the diabatic term is just balanced by the advection of the horizontal advection of buoyancy by the, so not horizontal, the two-dimensional. This is Jacobian in the YZ plane of the buoyancy, right? So here's your equation, and you can just change vertical coordinates, and instead of using Z as a vertical coordinate, you use B. And then this equation, which was in 2-dimension, becomes 1-dimensional. And it's so now you just have that the transport in the now vertical direction, but it's not vertical anymore because this y is not a fixed z, it's at a fixed b, so that the vertical or across isopycnal transport multiplied by the stratification balances the diabatic term. So here there's only the mean flow, it advects the mean buoyancy, and you, by just plotting the mean, well, the only stream function you have a good sense of what the diabatic sources and sinks are. So you don't need any machinery here. The Eulerian flow is good. It tells you everything about what's going on in the transport of, well, here was the buoyancy, but it could be another trace. The buoyancy is good because is a good tracer to work with because it's stably stratified, and so it's a good coordinate to change into if you want to change vertical coordinates, because it doesn't go through zero, it's not multi-valued. Yeah.
Is it on? Yeah.
Yes.
That this is the correct way to do essentially Manck's argument, because now you have the vertical transport but across an isopycnal balanced by the diffusive transport, which is this diffusive term I was talking about. He tried to make it in the vertical by simplifying, but that is the formal way to actually get the correct result.
Correct if you don't have any motion in the other direction or time dependence. Yes, we'll do that. There we go. So let's take another step. So now we're going to look at steady flow in 3 dimensions. So this is not going to be the observed ocean. It's going to be an idealization, is going to use numerical values in an idealization of the world ocean. Well, not even of the world ocean, but just of the Atlantic. Here it is. And we forget about the rest for the moment. But we put in this very important piece, which is that there's this region that goes around the world. And so it's not a completely closed box. It has an opening where stuff that comes in here goes out there. So it's periodic. So these are solid boundaries where you have no flow, and in fact not even no slip. Instead here stuff goes around periodically. Okay. And well, it's smaller than the Atlantic, but that's really not important. And then it's forced at the surface by wind, wind stress with a certain pattern, with westerlies, easterlies, as it is, and then relaxation to a prescribed value of temperature, which depends only on latitude. Never mind that. So if you did that in with good high resolution that resolved baroclinic instability in the ocean, which unfortunately occurs on rather small scales, 10 to 100 kilometers, you would not have steady solutions. Okay, you would have a time-dependent solution, and we will see those. But this instead was calculated. The computation grid was at 100 kilometers, so it does not resolve the baroclinic instability. And so these are parameterized, and I will spend a good fraction of a lecture explaining how to do that, but not yet. So take my word that there's some parameterization of baroclic instability, not that great, but you know, good enough. And there's some mixing near the surface in the top 50 meters, but then the rest is not really. The diffusion is, the mixing is quite small, and it's mostly provided by actually the advection scheme of the code, which is obviously necessarily a little bit diffusive. And here is just the surface temperature, how it comes out of the model, not what is prescribed, except it's prescribed to be almost zonal, but you see here there are currents that modify that. Never mind. This I will talk about this later, but here we're just talking about how to look at the results. Yes?
What about rotation?
Yes. Yes, this is rotating, and the rotation rate is 1 day. And of course it's 1 day near the poles, and then, you know, this I think was not done on the sphere. It's on Cartesian coordinates, but so it's on a equatorial beta plane. So the Coriolis parameter is 0 at the equator, and then it increases linearly at the pole to a rate which is, I think, about 1 day, right? Okay, so this is, yeah, it uses the beta plane. Now, so let's look at the zonally average stream function associated with the zonally average meridional and vertical flow, okay? And the units are Sverdrups, which are 10 to the 6 cubic meter per second. And that's the colors. And the lines is the zonally average temperature in degrees C, but here is 0, and then I think it's 1 degree contours. And what you see is this huge cell going this way in the southern hemisphere, and in particular in this region, which was that periodic region. And it's a cell because there is actually flow going in the opposite direction. Here is just in the top grid point only, so you don't really see it. But you only see the rest that is going like this. And again, this is the southern hemisphere. Get used to it. It's important. And so a flow that goes like this is a thermally indirect cell. Okay, because this ocean, as you see, is stably stratified. So it's warmer here than here. And so this cell, you would think, transports heat towards the equator. Not a good thing.
So, but it's colder close to the equator, or?
No. The colors is transport.
Okay.
And so this is a cell going like this. And this is a cell going like this. The colors, I know it would have been better to do colors, temperature, and contours now that I think about it. But this is not what it looks. I'm sorry, this was done the other way. And so the colors are circulation and the contours are temperature. So no, it's warmer at the equator. So the negative is, I don't know why it changed what this is. Maybe this, I know what this is. No, I know what this is. The dash is not negative now, remember. These are spaced at 1 degree, but here they're spaced at 1/4 degree, because otherwise you wouldn't get any contours, because it's more weakly stratified. So anyway, this is the picture that you get, and you get this cell that looks like this, which is plausible, but this one, it's implausible. And the reason is that here's the equation for the zonally averaged buoyancy equation, and this Jacobian is in the YZ plane. And so this mean flow is advecting the mean buoyancy, which here is the same as temperature up to constants. But then there are these other terms due not to time-dependent terms, because there aren't any, but due to departure, from the zonal average. Motions that has a zero zonal average. Waves, vortices, if there are any. Gyres, right? Gyres. When you have a gyre, the ones that the ones that Raf was drawing yesterday. Okay, okay. Whichever way it goes. This motion here has zero zonal average, and yet it will transport heat. In fact, when you see these departures from this zonal mean of the temperature is exactly because of those gyres. So you can tell here that there's a gyre going like that, and so it changes the structure of the temperature. Okay, so it's not true anymore, even if now if you change coordinates and go to the constant zonally average buoyancy coordinate, this term will become beautiful. It will become something like that, but then there's these other terms that are in the way, and so it's not true anymore that looking at the mean zonal circulation in buoyancy coordinates tells you what goes across buoyancy surfaces, because there's these other terms. Okay. So now what you need to do is start from the original equation before you average and change into buoyancy coordinate. Okay, but not the mean zonally average buoyancy coordinates, the full buoyancy coordinate, which depends on x, y, and z in this case.
You always assume that it is steady, right?
Yeah, this is steady. I will do the time dependent one thing at a time. And so you change to buoyancy coordinates, and then the equation, the buoyancy equation, steady for the moment, becomes this, where there is this weighting factor, which is the transformation of coordinate dz db, or 1 over db dz. And of course, if this becomes 0, that is, if you are neutrally stratified or even worse, negative, then you're in trouble. But buoyancy usually is stably stratified, and so you're good. Now, after you've done this transformation, then you zonally average at constant buoyancy, and now you see you have a sort of one-dimensional balance like you did before, and you can define a residual stream function based on this sort of incompressibility equation, where the residual stream function, now indicated by psi dagger, has its vertical, not vertical, but the derivative with respect to buoyancy is given by, is the thickness weighted average, that's what it's called, and the meridional at fixed buoyancy derivative gives you the diabatic terms. Okay, and now you can plot it, and here it is, and that cell that was sitting here is gone. Okay, now what you see is one big cell going across the hemispheres, across the equator, encompassing the whole hemisphere, and flowing, not everywhere, but mostly. So now this is in buoyancy coordinate. Flowing, at least in some parts, horizontally, that is along buoyancy coordinate. Now, if you want, just to sort of connect with what we were doing before, you can partition it in the mean part and the leftover, the residual. And so in some sense, what you are, and this, I'll have to explain to you that this is a slightly different way of doing the mean, because this is the mean in buoyancy coordinates, and the difference. So let me just explain that little difference. Okay, first of all, okay, how do you do this in practice? when you have your output or data in level coordinates, and you need to put them in buoyancy coordinate. So what this means by the average in buoyancy coordinate,
What do you mean by level coordinate?
level means at a fixed height, z level. This model is in level coordinates, not in buoyancy coordinates. So you have to. And so what you need to do is you integrate in dz and weigh your velocity by a Heaviside function that has to capture the values below the target buoyancy. So so you want a buoyancy at 0.01. You want to know the stream function as a function of latitude for buoyancy value 0.01. So what you do, you take the you weigh your your velocity by a Heaviside function for all those buoyancy less than 0.01. Sorry, did I say 0.01? And then you want it at a different buoyancy. You do that again, and you weigh it by all. You only capture the velocity below that value, and you keep doing that. And it's only after you've done that that you take the average. Okay. So you can do the same with the mean stream function. And so here you take the average, the zonal average, and then you weigh it by the average of the Heaviside. That's different, okay? Because here first you take the average of the Heaviside and the velocity, and here first you do the multiplication by the Heaviside, and then you do the average. And this is what was shown before, and that's different than taking the zonal average, that the first picture that I showed. But that's a technical. But just to explain why they looked different.
Question?
Oh, sorry.
So these buoyancy coordinates, are they including diabatic sources? Or
No, the
or so are we
buoyancy
taking
coordinates.
mean?
The buoyancy coordinates are is just a coordinate. So what you do is you look at your output and you say, what is the range of buoyancy that I have? Buoyancies that I have. In this case, it's easy because we prescribe temperature at the surface or relax to some value. So we know what the minimum buoyancy and maximum buoyancy is going to be. But if not, you just have to look at your output and see what is my minimum buoyancy, what is my maximum buoyancy.
What if you have regions that have sources?
Doesn't matter. It
would
doesn't matter.
still-
No, it doesn't matter. It doesn't matter. So this, it doesn't matter. So this, you just know that your buoyancy goes, say, from 0 to 1, just to make things simple. Okay, so now you want to know. Can I answer it first? Can I finish answering this question? Yeah. So you want to know, for example, what is the stream function as a function of y for the target buoyancy b equals 0. So you look and, well, there's not going to be any below 0, so that's 0. Okay. Then you go a little bit up, 0.1, and then you say, okay, what are the values of b less than 0.1? And you weigh your velocity as you do the integral in z by all the values that are below 0.1. And you have to look for them. It's a three-dimensional surface that you have to have mapped. So in practice, what you do, you interpolate your velocities onto buoyancy coordinates first, and then you do this weighing, and then you do this integral. Okay. And once you have that stream function, if you take its y derivative, that will balance all the sources, the diabatic sources. Okay. So in some sense, when you look at this diagram, which is in buoyancy coordinate, when you see something that goes like this, which is, right? that tells you that you're crossing buoyancy buoyancy surfaces, which is this region here, and so you have to have a diabatic sources that is balancing that. But when you do your diagnostic calculation, you don't need to know where they are. Yeah, it's just a change of coordinate, a painful one because you have to do it in 3 dimension plus time if you have time. So you have to do that for all your gridded field at every time. And of course you do this online if you have a time dependent code. You don't save all that output, otherwise where would you put it? Sorry, there was another question. Pardon? You answered it. Okay. Right. Okay, now unsteady flow. So now same geometry, same forcing, but now the resolution instead of being 100 kilometers is 5.4 kilometers. And then we put a little bit of explicit diapical diffusion, and there's no, that's it. There's of course friction, and now what is shown here is the mean time average surface velocity and time average vertically integrated stream function. So that shows you the gyres, and it's not too different. I'll talk about the results of this model later, but here is just for the diagnostics. So now it's the same thing, except that you have to take the time average. So the first thing you do is you take your field, your 4-dimensional field, you weigh it by the heaviside function of your target. Now this is just, these are numbers. This is your new coordinate. And you look at all the values of buoyancy in space and time that are below that value. Then you take the time average, then you take the zonal average. And so again, here you have this, colors are is the stream function, and the contours are temperature at 1 degree, but here at a quarter of a degree. And there's this ugly cell which is gone when you look at it in buoyancy coordinates. Here you see it very well in the time mean. So this is the result of this. You can also, if you want just to compare to this field, you can also remap it if you want in buoyancy coordinate, and this is how it looks. And you see that cell here in buoyancy coordinate, it looks like this. And the residual, which is the difference between these two, I shouldn't call it residual because this is called residual stream function. The difference is it's a cell that is in the opposite direction. Okay, and cancels that. Equivalent of the Ferrel cell, which in oceanography is called Deacon cell. Okay, so now yes.
The result here is remarkably similar than the one at a lower resolution that you described before.
Well, that's correct. This is yes, and yes, because the low resolution calculation was done after, and the parametrization, which I will talk how it works about later, but of course it has at the very least one free constant, in principle more, but in our case that free constant was chosen to match as well as we could the results of the high resolution model. Yes.
Quick question about the Deacon cell.
Yeah.
In the ocean, in the Southern Ocean, there's wind-driven. That's the part that's quite different from the atmosphere, because the atmosphere, the Ferrel cell is not really wind-driven.
No.
So how does this model deal with this part of the decant cell? Is there like a constant force?
Yeah. I'm sorry. I should have been more explicit here. The forcing is the same as the other model. The low resolution model, but there is wind. In fact, you can see there are gyres here, right? Here are easterly winds. Here there are westerlies, and then the westerlies go back to zero at the boundaries. So there's, the main source of energy in driving the flow is indeed surface winds. This is how this model is forced. There's both winds and surface temperature prescribed at the surface. The wind is at the surface, and yeah.
I have another quick question.
Yes.
You have this, the next slide, you have this enhancement, or how you're going to call it, to higher buoyancy levels in the subtropics of the gyres. Is that due to eddies or due to the diffusivity? Compared to your low resolution, where does this come from, right? Your low resolution model had basically a straight line, and these not.
Okay, let me check.
Oh no, it's curved.
So you're saying that these
Yeah,
were
right, exactly.
these are yes, they are quantitatively different, but so you're talking about these guys.
No, the upper part of that. So
Yeah, those
that
are
structure.
Yeah. So these are, in both cases, they are what we call the subtropical cells. So what it is that right at the surface, you have Ekman transport going in this direction. No, wait a second, let me think about it. Yeah. So, yeah, the flow is like this. So you have, this is in the region of easterly, so you have Ekman transport going poleward. And then the geostrophic flow right below, but not very far down below, returns that Ekman transport equatorward. So they are really the analog of the Hadley circulation driven by the surface winds. And in fact, they transport the same mass, more or less. But because the density of the ocean is so much larger than that of the air, their transport is much weaker than their volume transport, if you will. I suppose it's the mass transport. So yes, they're like the little Hadley cells of the ocean.
So if one believes the surface flow, surface current is driven by wind, so why would it be surprising to see the equatorial flow as a high latitude would be counterintuitive? I guess I did not say it very clearly. So
no, I think I know what you're saying. You're saying still there is wind here.
Yeah.
But so why is it that there is the flow is almost zero there?
I guess, if you follow the argument of the Fourier circulation, you are saying, the equatorial transport of the Fourier cell seems like artificial in terms of the heat flux. But if the ocean circulation, at least at the surface, is driven by the wind, so perhaps it is not very surprising to see the equatorial heat transport.
Right. This is in this coordinate system. But you see, we're now looking at a different coordinate system. So you're looking at a constant density. And the densities have, some of them actually come to the surface in the Southern Ocean, and they don't come to the surface, in a zonal way. They come to the surface kind of tilted. So when you have that, you only get some wind up to a certain point, and then there's another term which I will show you what it is form stress that really matters very much. In fact, that's that's, that's what's happening next after I explain how the diagnostic is done. Okay. So one last thing is that I find these graphs in buoyancy coordinate very difficult to read, because normally we're interested in what is happening in high latitudes, not near the equator. And at the equator is where you have a big range of buoyancy, and so your scale is very expanded, right? So here in high latitude, you're looking at, very small changes in buoyancy. And so in this buoyancy coordinate system, the high latitudes are squeezed in a tiny little bit, and I can't see a damn thing. So, so you can remap. Now, maybe I didn't go through that. Oh, yes, there it is. You can also look at the mean height of the buoyancy, right, surface. In the same way as the buoyancy can be a function of z, now you have z as a function of buoyancy. And you can look at the zonal and time average height of your buoyancy, okay? And it's calculated just in the same way, except that here the weight is 1. Okay, so now this represents the average height of your buoyancy B. Average in this case in time and zonal average. So now you have your stream function and you have your average z, and you can replot psi, or rather remap psi instead of its natural coordinate b into this average height. Okay, and then when you do that, you see what is happening in high latitudes a lot better, and it sort of is easier, I mean, at least for me, that we've grown up for many years looking at latitude depth plot, and so it's, I don't know, I just find it easier for human consumption, and so that's another possibility. And so yeah, right. So now so now there is so I've shown you how to do it in practice, but there's actually a systematic way of deriving all this that shows that you actually can rewrite the equations of motion, at least for the primitive equations, that is Boussinesque, non-hydrostatic, incompressible. Oh, did I say non-hydrostatic? Sorry, hydrostatic, incompressible equations in terms of only that velocity that is averaged over isentropes, and then of course if you want to have it dimensions of velocity, you divide by the average weight. Okay, and you can write the full equations in 3 dimension plus time in terms of only these thickness weighted average velocities, and you can write them in either buoyancy coordinates or Cartesian or spherical, whatever is your domain. And this was done quite recently by our own Bill here in a paper that has maybe what, 1 figure, two, 1 figure and 120 equations, something like that. But it's very clear. It is very clear. And I actually have it downloaded on my phone because I find myself always having to look at it. So, and I don't always travel with my laptop. So, right. So I'm not going to derive it because 120 equations. No way, Jose. But I will give you the results. And for details, you got to read the paper. It's not hard. It's just long, but long because you have to do it carefully. If you want to understand it, you gotta redo the calculation. And so I will just give you the results, and I give them to you in both buoyancy coordinates. There they are, and I will go through and then later in Cartesian coordinates. So, and the result is, well, number one, you can rewrite the momentum equations in terms of only the residual or thickness weighted average velocities. And here is sort of, so this is the tendency. This is the vertical, equivalent to the vertical advection, but is in fact advected by, remember that here the vertical term is the diapicnal term, right? And then this is like the Coriolis term. Well, this is just written in vorticity form. You can write the equations in many forms, but this is the vorticity form. So this is the Coriolis term, and this is it's like the thickness of a shallow water system, but in fact is sigma is 1 over dB dz. And then this is like the Bernoulli function, the equivalent of the Bernoulli function. M is Montgomery potential, and here are the mechanical forcing or friction term, and then all the eddy terms are in this divergence of these EP fluxes. And here I give you an example of one component of the EP fluxes, and it is correlations of velocity, and these are vectors in the x direction, the y direction, and this is E3 is in the vertical direction, and you will recognize them maybe a little bit from before. This is equivalent to b prime v prime over n square, but here is you have the height, and instead of the v you have the Montgomery, the pressure gradient, the Montgomery potential gradient, and here that term that was b prime over n squares, if you remember the PV terms. And that's the only place where they appear, in the momentum equation. And then this is the hydrostatic equation, and here's the buoyancy equation. So you have, all you have is the thickness weighted velocities, the diabatic effects. This is the diabatic effect. Like in our case, in the ocean would be just diffusivity, diapicnal mixing, and in the atmosphere you would have diapicnal mixing and maybe OLR. And everything is in terms of the thickness weighted velocity, and of course there's departures, the eddies. We need to know those, right? It hasn't solved the closure problem of how we parameterize eddy fluxes, right? They're still there. But they're all confined to the momentum equations. And some quantities are averaged, just averaged, and some other quantities are thickness weighted average. But, like for example, the pressure, Montgomery stream potential is always average, as is the height, whereas these velocities are thickness weighted. But they only appear in one way. There's not a mixture. And so the important thing, the breakthrough to derive these equations is to realize that when you go into buoyancy coordinates, you cannot use an orthogonal system. So for example, if you decide that your coordinates are along buoyancy surfaces, like these are E1, E2, so this is along a buoyancy surface, then the third component would not be the one orthogonal to the buoyancy, would be the vertical one. And conversely, if you want to use your original, say, Cartesian coordinates, then the third component would be that normal to the buoyancy. And so you have to use a dual basis vectors. And then if you do that, Then you have a way of doing calculus, div grad curl. Here are the rules. So for example, for divergence, you use I never remember if these are called covariant or contravariant. Nobody knows here either, so good. No, I'm sure Jacques does. And you have to take the gradient and the divergence and the curl in a certain way. So now you have your calculus in this dual basis vector system, and off you go. So this I've already said. So now I'm going to talk about an application of these equations, both for diagnostics and for actually using those equations to solve for the circulation of the ocean. And the first application is an application to the Antarctic circumpolar current region. And for those who are not oceanographers, I thought I would just show you what the Antarctic circumpolar current looks like. This is actually a model, but it's a current that goes around the Antarctic continent, and it's extremely unstable to baroclitic instability, and I'm sure other kinds of instability too. And so it's very complicated, and it transports a huge amount of water. So the amount of water that goes through here, well, the latest estimate is 170 spheredrups. That's a lot, and it has speed of about 1 meter per second at the surface, and it's really massive. Not very easy to not very easy to keep instruments in the water here. Measure one of the challenges of actually measuring the transport here for a long time is being able to keep instruments there and not being stripped away. And not to mention going there in winter, austral winter. So this paper, which I thought was kind of nice, very carefully analyzed the balance of forces in a high-resolution model. Does it tell me what simulation? I don't remember. Well, I don't remember what the resolution is. Maybe it's written here, but it's very high. And so this is like a very short segment of the Antarctic circumpolar current, only 1,000 kilometer long, and it only goes for 2,000 kilometers, and it's forced by the wind at the surface and a pattern of temperature so that the flow is stratified. Yeah. So and it doesn't even have salinity, it's only temperature. And the equation of state is just linear, so the buoyancy is directly proportional to temperature. And so, so again, it does an analysis of these terms in a diagnostic way, and so this is just a repeat of the equations. And so, okay, so first of all, thickness weighted average. Okay, so the definition, remember, of thickness weighted average is that you weight by dBdz, or 1 over dBdz, or dZdB, and then you divide by the average of sigma. So you might be concerned what happens at the surface where the thickness, in some sense, goes to 0. Are you going to divide by 0? And the answer is no, because that average is the sum of all the values of these thicknesses wherever you are. And as long as you have at least one of that values, and if you don't have one of those values, then you wouldn't really be doing that, then you just weigh by that and divide by how many values you have. And if their thickness is 0 because you're at the surface, then the value of u is 0. Okay, but so it just to show you that it works. And so again, here is a plot of the meridional velocity as a function of latitude and buoyancy. And you see where it's blue, it's negative, so the cell is like this. There's a cell near the surface, which is like this, flowing like this. Then a cell near the bottom, which goes positive, so it goes like this. And in the middle, there's essentially nothing. Okay, there's nothing. And now, someone before was asking about the Ekman transport. So the Ekman transport here near the surface would be in this direction. So, but the residual flow is in the opposite direction. So how is that possible? Why does that happen? And so Todd Ringler, who wrote, and his collaborators who wrote this paper, really did a very careful analysis of what it is that is going on there. And so they did an analysis of the U-momentum balance and look at what is happening in that layers, which is only 230 meters high. So just to clarify, so what they're doing is that they're taking this box, averaging this box in this direction, and then look at it as a function of depth or buoyancy. Okay. So if you had a balance between the wind stress and the Coriolis term, this term would be on the other side. Okay, so the wind stress is this term, and the Coriolis term would have to balance it. It would be on the other side. And instead is on the same side. Okay, and that's because this eddy term coming from the divergence of the Elias and Palm fluxes is huge near the surface. This is an eddy resolving model, okay? It's more than twice as big. Okay. And so surprisingly, this is not at all what we would call Ekman balance, because this would have to be of the opposite sign. Instead, there is this huge eddy force coming from this term. And then, as you go down in the water column, you have a balance between the Coriolis term, the eddy force. They almost exactly cancel. And so from 230 meters to about 4,000 meter, you have nothing in the residual framework. Nothing at all, and not until you go back to the bottom.
So may we call this a turbulent Ekman layer or not?
Oh, well, I think it is. I'm sure it is. But maybe similarly, it's been erased to that situation where the sum of the mean and in horizontal convection, the sum of the mean plus the eddy flux was very small. Here it's also very small, the residual, right? And so what's going on? So now we look at this mysterious term of the Elias and Paul flux. So it turns out that of all these terms, the most important one, the one that has the largest component, is this term here, which is called form stress. And I will talk about that later, but it's just a correlation of the height with the Montgomery potential gradient. This is like the pressure. So it's very similar to the form stress that you have against a mountain, right? So if you have a mountain and you have a mountain here, and then you have a pressure surface, a pressure line, and that line, continues here, and then you have a different So this is P, and this is the height of your mountain, eta B at the bottom. So you have a different pressure here than here, then you're exerting a torque, and that can accelerate or decelerate your flow. So this is quite similar to that, but instead of being a solid mountain, it's an isopycnal surface, B equal a constant. And then you have a pressure surface which is not in quadrature, as long as it's not in quadrature with it. Then you have, as long as it's not aligned, the gradient is not in quadrature, then you have a form stress. So that's what this term is. Okay, so zeta is the height of that buoyancy, and m is like the pressure and gradient. And so now he plots this term as a function of, again, of buoyancy and latitude. And the essential point here is that, in fact, it's even since E3, remember now in buoyancy coordinates, that's actually the vertical dual coordinate system. So we got to go back and look at it in the vertical. And you see what is happening is that it's essentially independent of height in the middle. The only place where it depends on height is in the surface boundary layer and bottom boundary layer. And in the middle is not that you don't have eddies, you do, and they even have form stress, but it has no divergence. Okay. The only place where you have divergence is in the surface diabatic layer and in the bottom frictional layer. So that's why in these calculations you were seeing from here downwards nothing, because really you have d by dz of this term, and it's, although it's non-zero, it has vertical, it's vertically uniform. And for those who know about ED problem and baroclinic instability, that's an example where you have this term v prime b prime over n squared. It's non-zero, but it's constant in z. It's a very similar thing.
Is this on? Can I imagine this as vertically propagating eddies, or?
No, I don't think so. No, I think they are probably propagating with the mean current, but I don't think they're vertically propagating. If it's like ED, they're not really vertically propagating. Ah, there was form stress. There you go. I had it.
Another short question.
Yeah.
Is it more like can I think about like a barotropic thing? That is probably so. If they only diverge at the bottom and create at the top, they propagate the signal from the top to the bottom, and it's very relatively quick, right? Can I think about it like that? The vertical structure of these eddies are not changing with height in the interior.
No, excuse me. No, the eddies themselves do have a vertical structure, but it is the correlation that doesn't. So, for example, in ED problem, which I think we did in class,
Yes,
Mommy. For example, there you have Q prime equal to 0, right? Because ED's problem has Q equals 0. And so obviously Q prime V prime bar is equal to 0 since Q prime is 0. And so since this is minus d by dy of U prime V prime bar plus F naught square, well in ED's case n square is constant, V prime B prime bar, that has to be 0. Now in ED's case, this is 0 because the fastest growing mode is the one that has L equal to 0. Oh, d by dz, right, thank you. So this is 0 in ED's problem, at least for the largest growing mode, because L is equal to 0. So you see this is 0. It's not that V prime B prime is 0, it's just that it's vertically uniform. But if you remember V prime in Edie's problem, this is the stream function, right? This is Z and this is X. It's not 0. It has a vertical structure, but this correlation is, yeah, exactly there. Well, but they're phase locked in this way. I mean, so are these. And I don't think there's any vertical propagation when you look at a movie of eddies. Eddies, they just go like this, right? I mean, that's my paradigm. I don't know how it's the details here. Okay, I'm done for now.
Do we have more questions?
Yes.
Can you
More
repeat
than
the
no,
question?
I don't think that's no. I think that's not true, actually. Oh, sorry. The question was, can we say that QG is vindicated from this diagnostic because this is a dominant term? No, I think what is here you have, I think ED is vindicated, but what I think is not at all QG here is this part. This part is the part that is not QG at all, because for this part it is essential that the isopickles are outcropping and producing this huge, you wrote a paper on this with Clocker. Yeah, the compensation here, this part, yes. But this part here, in this part here, there is this huge form stress against these outcropping surfaces that produces this eddy force that completely destroys Ekman balance in buoyancy coordinates.
Okay.
Yeah.
Are these results significantly altered by the fact that you took TWA instead of TEM? Or would we have learned the same thing had we done it in TEM?
Well, that was essentially Ralph's question. And the answer is, I think, yeah, I think, no, this is the diagram that I want. I think from here down, you could have done it with TEM. But from here up, no. From here up, you need the full variation of the full excursion of isopickles, because here the isopickles cannot be approximated as horizontal at all. They hit the surface. And this term here would not be so large, I think, because, you know, if you don't have outcropping isopickles near the surface, you wouldn't have such a big form stress. Yes, there's someone here.
A similar situation can also be seen in the atmosphere because the isentropes themselves
hit the ground.
Does it make more sense to use this in that framework as well?
Absolutely.
In this model of this ACC, how do you create this stratification with the isopickles that reach the top? Like, how do you which initial condition do you use?
Okay.
Which forcing do you use?
So let me first say that the initial conditions here are irrelevant in the sense that this has reached statistical steady state. And I will talk about how you make stratification in the ACC. That will be lecture number 2 or 3, depending on how fast I go. But let me just say, just so that you know you don't get a panic attack until I tell you, an anxiety attack. But the physical idea is very simple, and that is, you have this decon cell which is thermally indirect. So now you imagine here we're going from cold to warm, and so, and this Ekman transport is pushing the cold water on top of the warm water. And so if there was nothing else, you do a thought experiment, you tell baroclinic eddies, nobody moves, okay, for the moment. So we only have the mean flow, but we allow convection. Then this cell will tell to make isopycnals vertical. Okay, so you have a gradient here, you're pushing cold water over warm, and then they convect and they become vertical. Okay, and now baroclinic eddies say, hey, a lot of available potential energy. I can grow very quickly and very nicely, and that's what they do. They remove that available potential energy, and they make the isopycnals less vertical, right? They re-stratify, they slump them.
Okay, thank you, Paola.